Welcome back to Pike Mathematics. Today I want to talk about vector fields. So let's get started. I prefer to work in paper, so I hit New and Paper. All right, vector fields. What are they? Vector fields take points in space and assign vectors to those points. So let's take a look at an example. We'll make this vector field a function of x and y. We'll make it equal to negative yi plus xj. And so we're working with vectors, so I have to tell Iota that. I go to Sidebars, Math, and I select Classical Vectors. And then I like to put the hats on the unit vectors. Enter. Okay, so that's my vector field here. For me personally, it's difficult to look at this and kind of understand what the vector field's doing. So I think one good solution is to go ahead and graph it, and then you can gain a little more understanding about the field. Insert function, and so I have to select field. Okay, I've already defined the function, so I'm just going to call it v of x and y, and then we're going to hit test and take a look at it. All right, so there's our field. You'll notice this division box and scale factor. The divisions are kind of how many vectors across and how many vectors down the graphic should be. And the scale factor, that's we actually have to make the vectors smaller so they don't overlap as much, and it makes a better picture. But I'm going to change these. I'm going to change the divisions to 10 and the scale factor to 2. And then we'll see what it looks like. All right. So now you've got this graphic. We can kind of understand a little better what this vector field's doing. Um, in particular, it's got this kind of counterclockwise rotation to it, and then as you move away from the origin, the vectors are actually getting larger. Let's go ahead and look at another example. I typed out all these equations already, just to move things along a little more quickly. Look at this vector field big R. Let's go ahead and graph that, see what it looks like. And select field, big R of x and y. Change the color for fun. And there's our vector field. And again, I'm going to go the divisions of 10 and 2, the 2 for the scale factor. Let's see what we get. All right. So in this vector field, it has that similarity with the last one, where that as you move away from the origin, the vectors get bigger. But there's kind of no rotation to this field. These vectors are simply pointing straight out from the origin. Well, I want to play with this field a little bit. I want to make it similar, but I want to make a vector field where each vector only has a magnitude of 1. And to do that, so you can see the magnitude of r is the square root of x squared plus y squared. So if I divide this field by that, I'll get unit vectors. And so I can get this vector field little r. So again, if I just divide by the square root of x squared plus y squared, I'll get what I'm looking for. But there's another way you could do this, and same result, but I just kind of like the look of it. I think it's a little more elegant way to do it, and that is to use the norm function that we have in Iota. And to use the norm function, it's backslash NOR, and then now we have to reference the vector that we want the magnitude of, and that's big R, the function of x and y. And then you have to kind of close out the norm function. So backslash NOR. There we go. And anytime you make a change to one of these equations, you have to go back to Iota and hit refresh. There you go. So there's our field. We're going to graph it to make sure it looks the way we want it to. Let's see, function. And it was r of x and y. Make it yellow. There we go. So similar to the above graphic, but now each vector only has a unit length of 1. Well, what would happen if I changed the sign here? Again, I have to hit refresh, regraph it. Aha. So now we've changed the direction of those vectors. Now they're pointing directly at the origin. So why did I create this vector field? I created it because I want to create a gravitational vector field um, uh, created by an object at the origin, and I need these unit vectors to do that. But I also need to know how what the magnitude of the gravitational force will be. Luckily, Newton has already figured that out for us. So the magnitude of gravitational force is you have the big G gravitational constant times the mass of the first object times the mass of the second object divided by the square of the distance between those objects. Again, that's the magnitude of the force. So if I attach this magnitude to these vectors, I'll get the gravitational field that I want. So we're gonna call it g of x and y. It's going to be equal to F times little r. There you go. That's it. Now, G and both of the M's, those are just scalars. So we're going to make our life a little easier. We're going to make those equal to 1. Okay, and then I'm going to hit refresh again. Okay, so let's graph G here and see what it looks like. Insert graphic. Let's see. I can make this one green. See what it looks like. There we go. So again, we have an object here at the origin, and this is the gravitational field that object is creating. And so you can see that because gravity is an attractive force, the vectors are pointing at the object. And then you can see that as you move away from the origin, the vectors get smaller and smaller, and they get smaller rather quickly. And that's because of the inverse relationship, the inverse square relationship of the gravitational force. Okay, now I think it's time to introduce some vector calculus. So we have an operator programmed into the Iota system, and you can call it by backslash NAB. That's for nabla. Okay, it's this. This is called the del operator. And the del operator, it looks and acts kind of like a vector. It's not really a vector, but it sure has kind of vector-like qualities. So when I make the del operator, if you have it operate on a scalar function, that's called a gradient. And what does it do? Basically, what the gradient does is it takes a scalar function and it takes the partial derivative of that function with respect to x and it puts it here. And then it takes the partial derivative with respect to y of that scalar function and puts it there. And similarly, it takes the partial derivative with respect to z of that scalar function and puts it there. So let's see how one get an example of that. Well, first I need a scalar function. So how about this one right here, big P? This is you'll probably recognize this as the gravitational potential energy. So let's see what happens when I take the negative of the gradient, and to do gradients, you do backslash GRA of P. What is that? What do we get there? There we go. You'll probably recognize this. That's the exact same equation, vector field we previously calculated. I wanted to show you this example because when you have conservative fields, it can be proven that there is a scalar function such that the negative gradient of that scalar function equals your field. And that's what P is here. P is that scalar function that when you take the negative gradient, you get the gravitational field right here. Okay, so that's a gradient. Let's try another gradient example. I pulled this scalar function here from Mary Boas's Mathematical Methods in the Physical Sciences, the third edition. This is page 292, chapter 6, example 2. So this is a function where you put the points in space in there and it tells you what temperature is there. All right, so we can take the gradient of T. So backslash GRA T equals that. Okay, so you put in this, the del operator operates on the scalar function and it returns a vector. Well, I'm going to call this big H. It's going to be a function of x, y, and z, and I'm going to make that equal to the gradient of t. Okay, so same vector field here, but now I can take specific points and plug those in and find out what the gradient vector is at those points. And the point that Mary Boas uses is -1, 2, and 3. So h of -1, 2, 3 equals, we get this vector. And so what is this telling us? When it comes to gradients, the direction that this vector is pointing, that's the direction in which the scalar function is increasing most rapidly. So in this case, the temperature is growing most quickly in the direction of this vector. Here's another interesting thing you can do. You can take the norm of that vector. Let's see what we get. 8.31. That's actually the square root of 69. What that is that's how much the temperature is changing in the direction of this vector. So we learned quite a bit of information about this function by taking the gradient. But so far, we just know what it's doing in the direction where the temperature is increasing most rapidly. What about in other directions? Well, there's something called the directional derivative that you can do that is also very useful. And the to do the directional derivative, you basically do a dot product of this vector, the gradient vector, with some unit vector. And you'll recall that the dot product of two vectors is equal to the product of the magnitude of either vector times the cosine of the angle between them. The nice part about doing a dot product with a unit vector is that the magnitude of the unit vector is 1. So all you really need to do to find how the temperature is changing in some other direction that isn't the gradient vectors, you take 8.31, that's what we got here, times the cosine of whatever the angle is between the gradient vector and the vector we're interested in. So let's say we want to know how is the temperature changing 45 degrees from the gradient vector. There we go. It's 5.88. That's the change in the direction of that unit vector that's 45 degrees off from the gradient vector. What about 90 degrees? How is it changing? Turns out it's not changing at all. It's 0. Okay. So that's the gradient. Did a couple examples there. So the del operator can also operate on vectors, and when you do that, you can basically kind of do almost a dot product with another vector. And when you do that, it's called the divergence. And so here's a vector field here. We're going to go ahead and figure out its divergence. Remember, when you do dot products, your result is a scalar. So the divergence takes a scale vector field and returns a scalar. So to do divergence, it's backslash div of v equals that. So if you had a point in space and you plugged it in there, you would just get a number. Well, what does that mean? The way I kind of most often hear it explained is in terms of, say, flowing water. If you had a positive number, that would mean that more water is flowing out of your point than is flowing into it, and they call that a source. If you have a negative number, that means more water is flowing in than is flowing out, and they call that a sink. And if the result is 0, that means just as much is flowing out as is flowing in. All right, so let's do another divergence. And for this example, I wanted to use this equation. This is the equation for a magnetic field where you have a kind of infinitely long wire that's running along the z-axis, and it has a steady current that's running in the direction of the positive z-axis. Now, this is actually in cylindrical coordinates. This is phi hat, so we'll have to kind of convert it a little bit. But just a little bit more about this equation. The I here, that's a constant, so the current's constant. 2 pi, that's a constant. Mu naught, that's the permeability constant. But the only thing here that isn't a constant is s. That's the distance from the wire, and so it's actually equal to the square root of x squared plus y squared. Just in this aside, this mu naught, the permeability constant, we've got a number of constants that are already programmed into Iota. If you click on it, you can see that's how you call it. At mu0 gives you the permeability constant. If you wanted, for example, the permittivity constant, you just go at E0, and there's the permittivity constant. Okay, so back to this field, we need to convert this back to Cartesian. Right now, it's in cylindrical coordinates. This is what that phi hat looks like. If you want to, you can basically substitute that out with this uh, unit vector v, and so we can then get something like this. We can redefine this as a vector field b, and again, mu naught I and 2 pi, those are all constants. We're just going to treat them like they're equal to 1. The thing that I can't treat equal to 1 is s. That's equal to 1 divided by the square root of x squared plus y squared. Okay. And then if I take that, and multiply it times v, that is going to give me my, let's see here. All right. So that gives me my vector field, or not my vector field, my magnetic field that's created by that infinitely long wire that runs along the z-axis with a current that going in the positive z direction. So let's go ahead and we can graph that. There we go. So what you can see here is that, I mean, imagine the wire is kind of coming out of the page, and that's also the direction in which the current is flowing. You can see, and this kind of makes sense, the magnetic field kind of wraps around, swirls around the wire, and then as you move away from the wire, the magnetic field decreases. Now, it doesn't decrease as quickly as the gravitational field because it's only inversely proportionate. It's not inversely squared proportionate. Although it can be a little confusing if you look at this, because this looks like it's inverse squared, but the reality is you're taking x squared plus y squared square root times the square root of x squared plus y squared right here to get what looks like the magnitude squared. Okay, let's take a look at something else here. So that's we've figured out the magnetic field around this wire. What happens when I take the divergence of this magnetic field? There you go. It's zero. That's one of, you may recognize this as one of Maxwell's equations. The magnetic field, the divergence of magnetic field is always zero. If you go back to what we talked about earlier, what is the divergence? You get some number, and it's kind of a measure of how much is flowing out and how much is flowing in. Well, it turns out with magnetic fields, the magnetic field lines that are going out are equal to the magnetic field lines that are coming in. So you always get zero. All right, so that's the divergence. Let's talk about curls next. The curl is kind of like taking a cross product between two vectors, where the first vector is that del operator again. But what does it kind of mean? It tells us something about kind of the swirling or curling nature of our vector field. And specifically, it can tell us something about how quickly the field is rotating and the axis about which it's rotating. So let's try a curl real quick. We'll try to call the curl, you do \CUR, and then we'll do this field that we've talked about a little bit already, negative YI plus XJ. What is that curl? Okay, so it's 2K, and we've graphed this one earlier, remember? That's what we graphed. So what is this telling us? Well, it tells us two things, actually, just from looking at it. Because we only had this K unit vector here, it's telling us that this field is rotating around the z-axis, and you can see that here. by looking at this graph. It's rotating around the z-axis. The other thing it's telling us is that the magnitude of this vector, which is 2, is actually twice the angular velocity. So the angular velocity is actually 1. And so if you look at this graphic again, if you could think of this as like a kind of a rigid disk spinning, while these points have a larger instantaneous velocity than these points, they're all kind of rotating at the same angular velocity, which in this case is 1. We're going to try another curl. So backslash CUR of, say, X I plus, let's see, YJ. What does that give us? 0. Okay, this is I think we graphed, this is the first vector field we graphed. Yes, this one right here. And you can see, again, the curl kind of gives you that measure of how much the field is rotating. And you can see there's kind of no rotation around an axis. And so that's why it kind of makes sense that the curl there is 0. One thing that's kind of cool about curls is that the curl of a gradient is always 0. And so you can kind of see that here. If we took the curl of that gravitational field, let's see what we get. It's 0. Because remember, that gravitational field was actually a gradient itself. It was the gradient of the potential. So the curl of a gradient is always 0. So for those of you that haven't taken electrodynamics yet, if you have a static electric field, it is the static electric field is equal to the negative. There is a scalar function such that the negative gradient of that function is your static electric field. And so if you're ever asked on an exam, is this electric field a static electric field? If you took the curl of it and it was non-zero, then the answer is no, it's not a static electric field. Because if it was a static electric field, it's equivalent to a gradient, and the curl of the gradient would be 0. All right, last thing I want to talk about real quickly is the Laplacian. The Laplacian is basically a second derivative. What it does is it first takes a gradient of a scalar function, and then it takes the divergence of that vector field that it's created. So let's look at, we're going to do a Laplacian real quick of something we already worked on, and it's backslash LAP of T. Let's see what that looks like. Remember, that was that temperature function, right? So the result was 0. Now remember, we'll go back to that temperature function here. See, we know that kind of throughout space, the temperature, according to this equation, is changing, right? But what is the Laplacian here telling me? Well, remember, it's really the Laplacian is a divergence itself. So what happens when we have a divergence in 0? That means whatever's flowing in is equal to what's flowing out. And so what this is telling us, this gives us a very interesting additional piece of information. It's telling us when we have that scalar function t, that even though the temperature is changing all throughout space, what it's saying is that at any given point, the heat must be flowing, right? Because we have hot points and cold points, and so heat must be flowing. What it's telling us is that at any given point, the amount of heat that's flowing in is equal to the amount of heat that's flowing out. So the temperature at any given point isn't actually changing with time, even though the temperature is changing with distance. And so the Laplacian gives us that very interesting insight into that function that we didn't have previously. I think that's about all I wanted to talk about today. I appreciate you taking the time to watch us. I hope you found this interesting and educational. Please check back in again for additional videos. Thank you so much.